this is 16.4b, Green's theorem continued. What we're going to talk about is actually Green's theorem in reverse. Doesn't exactly mean like we're going to take the idea, so let's just remind ourselves. Green's theorem, the idea was if we have some kind of a simple closed figure here, and we were to take and go around this thing counterclockwise, like so. And inside of here is your domain, and outside of here is your curve. We'll call this C. If you were to go around this thing counterclockwise, doing the line integral, you would be able to do the line integral of p dx plus q dy, which would be the same as the double integral over d of dq dx minus dp dy dA. So the idea is we're not going to go backwards. We're not going to go to the right. We're not going to go clockwise. We're going to keep this thing counterclockwise, but we're going to take the idea of going from the line integral to Green's theorem for going backwards and saying, well, if we have Green's theorem, maybe we can go backwards and actually do a line integral that's easier to do. That's the concept of what we're going to be talking about. Well, this really only happens if you have a special case. So let's define when that's actually going to happen. This only happens when dq dx minus dp dy equals 1. If that's the case, what we have is the line integral over a curve, closed, simple, no holes, of p dx plus q dy. Again, just going from this definition up here, would be the double integral over d. Well, if we let dq dx minus dp dy, which is this, equal 1, then I'm really just taking the double integral of 1 dA. Which, if you think about it, if I'm taking the double integral of 1 dA, all I'm really getting is the area inside of here. So I'm getting the area of d. Oops, d. Excuse me. All right, so when can this happen? When can we actually get that this dq dx minus dp dy equals 1? Well, there's a few simple cases that we could look at. First one would be is if we let q equal x and p equals 0. Let's go back up here real quick. If q is x, so this is x, and p is 0, well, if p is 0, this whole 0 dx goes away. So all I'm left with is a line integral of c of x dy, line integral of x dy, and that'll equal the area of d. Now let's see if that works. X dy. Well, dq dx, the derivative of this with respect to x, would be 1, because q is x, right? So dq dx is 1, dy, and dp, and then the p part is gone, so that's out of there. And then dy, because p is 0, is just dy. So you would get this, which does give you the dq dx minus dp dy is 1. Another case would be is let's let p equal, now in this case it would have to be negative y, and q would be 0. So again, if q is 0, this part right here goes away, so there's no dy. This one right here would have to be negative y, because up in this formula right here, if I took the derivative of p with respect to y, the derivative of p with respect to y, that's negative 1. So what you would get is, because dq dx would be 0 minus the minus 1, that would equal 1. So that's another way to do it, and that would give us the line integral over c of negative y dx. Again, that's the area of D. Now, these are two very trivial cases, and this really isn't going to be the most commonly used one. The most commonly used one that we're going to look at is number 3. This is the one that's going to really help us out. Is if Q were to equal 1/2 x and P were to equal negative 1/2 y. So then what you would get is the integral over c. We could pull the 1/2s out to the front of x dy minus y dx. And again, that's going to give you the area of D. And again, excuse me, you could check to make sure that this works. So dq, dp dx, let me try that one more time. So dq dx, the derivative of q with respect to x is 1/2, minus dp dy, which is the derivative of p with respect to y, that's negative 1/2. So 1/2 minus 1/2 does give you 1. So this is a special case. This works. And ultimately, what you really want to think of here is that as long as the coefficients of x and y add up to 1, the y part is going to need to be negative because you'll be subtracting it, and this would have to be positive. So as long as these two coefficients add up to 1, for example, this could be a 3/4, this could be a negative 1/4. This one here could be a 2/3, this could be a negative 1/3. As long as they add up to 1 when you subtract this one minus this one, this will work. So any combination of these two things is going to add up to 1, where the y part is negative and the x part is positive. This is going to work. All right, so let's go ahead and take a look. So we're going to examine the previous cases with a circle of radius 5. And we're going to need to do some parameterization to do the problem. All right, so first of all, we know that if we're going to find the area of a circle, here's our circle, radius 5. We know if we're going to find the area of a circle radius 5, we already know what that is. We know that we should get 25 pi, right? Pi r squared. So we know that this is what the answer should be. Well, there's 3 ways that we're going to do this. We're going to do it with the methods that we just showed above. So letter A, we're going to do the line integral over c of x dy. And then letter B, we're going to do the line integral of negative y dx. All right. And then we're going to need to then we're going to need to do part C, but I'm going to wait to write part C until the bottom of this thing. So we need to parameterize this. So we need to come up with the parameters. All right, one thing that you guys should hopefully know by now is when you're dealing with a circle, the easiest way to parameterize a circle is in terms of sine and cosine. And we know that x equals r cosine theta. Well, in this case, r is 5, so it's 5 cosine theta. And we know that, or actually, let's not use theta. Let's use t, since we're doing this in parameters. It doesn't matter. It's going to work out the same. Well, we'll use t, because that's what we're used to using in this. And then y would equal r sine theta, which is 5 sine t. And the reason that works is, again, if you square this right side, you would get 25 cosine squared. And if you square this side, you would get 25 sine squared. And then you would get x squared plus y squared equals 25 cosine squared plus 25 sine squared. Factoring out the 25, you'd have a cosine squared plus sine squared left, which is 1. So you'd get the standard equation x squared plus y squared equals 25, and that's your standard equation for a circle. So it works. You can check that if you're not sure. But we're going to need to have that parameterized. So now when we go to do letter A, we want to do So because of this is going to be in circles, we're going to do polar. So it'll be the integral from, let's see, we're going to go all the way around the circle, so it's 0 to 2 pi. And it's going to be x dy. X is 5 cosine t. dy is the derivative of y here, which is going to be 5 cosine t dt. All right, so you can pull the 25 out to the front. And then we've got cosine squared t dt. And cosine squared, we have to use our reduction formula, so it's going to be 25 integral from 0 to 2 pi. Remember, the reduction of cosine is 1/2 1 plus cosine of twice the angle dt. We can pull the 1/2 out to the front, and then we can start taking the antiderivative. So the antiderivative of 1 is going to be t. Antiderivative of cosine 2t is going to be plus 1/2 sine 2t. And we'll evaluate that from 0 to 2 pi. So we get 25 halves. Plugging in 2 pi, we get 2 pi. Plugging in 2 pi here, we get sine of 4 pi. That's 0. Plugging in 0 for both of these, sine of 0 is 0. So we get nothing there. So the 2's cancel out, and we get 25 pi, which is exactly what we were supposed to get. Okay, let's see if it works for this one. Well, it will. Let's just show that it works for this one. Okay, so again, it's going to be 0 to 2 pi. So we're going all the way around the circle. This is going to be negative y, so I'm going to pull the negative out front. Y itself is 5 sine t dx. Well, that's the derivative of this with respect to x. The derivative of 5 cosine t is negative 5 sine t dt. Well, the negative 5 and this 5 can be pulled out to the front with that negative, so I'll have a negative, negative, which is positive. 25 goes out into the front. And then I have a sine squared left over. And then once again, we have to use a reduction formula. So 25, integral. I don't like that. Let's just get rid of this. All right, so 25, integral from 0 to 2 pi. The sine squared reduction is the same thing as the cosine squared reduction, except that it's minus, so it's 1/2. Oops, what happened there? 1/2, there we go. 1 minus cosine of twice the angle dt. So then we get 25 integral 0 to 2 pi. Actually, let's get rid of that. We're going to go ahead and pull the 1/2 out to the front. So we'll get 25 halves. We'll take the antiderivative of 1, which is t. Antiderivative, again, of negative cosine 2 pi is negative 1/2 sine 2t. I think I said pi in there. I'm not sure. Should have been t. From 0 to 2 pi. So same exact idea. We'll plug the 2 pi in, so I get 25 halves times 2 pi. Plugging in 2 pi here is 0. Plugging in 0 to all that is 0. So once again, the 2's will cancel out, and we will get 25 pi. So it has worked for letters A and B. Let's double check now for C. This is the one that's probably more important. It's going to take a little bit more, I'm sorry, it'll take actually a little bit less space. So let's change colors. Let's go green. Whoops. Nope. I want to go green, but I want it to be much thinner than that. There we go. So letter C says we want to do 1/2 the line integral of x dy minus y dx. Okay, we've already got our parameters set, so let's go ahead and set this thing up. So we're going to have 1/2. Once again, it's still going all the way around the circle, so 0 to 2 pi. X, which was 5 cosine t, dy, which was the derivative of y, which is 5 cosine t, minus y, which was 5 sine t, times the derivative of x, which was, in this case, negative 5 sine t dt. And hopefully what you can see is this is going to simplify really quickly. I've got a 5 times 5 here, which is 25. I got a 5 times 5 here, with, excuse me, a negative 5 times a negative 5 here, which is also 25. So I can actually pull that out to the front. And that's going to leave us with a cosine squared t. That minus times that minus became positive, so plus sine squared t, which of course is just 1. So really what I have is 25 halves, the integral from 0 to 2 pi of 1 dt. And that's going to be 25 halves of t from 0 to 2 pi. Plugging in 2 pi, the 2 pi goes here, the 2's cancel out, and you get 25 pi. Plugging in 0 gives you nothing. So there it is. And this was much shorter, actually, than even doing the other two. That's just because the algebra involved with the trig. So you're probably never going to use Green's theorem in reverse, or Green's theorem in particular, to find the area of a circle. It just doesn't make sense. Okay, you're not going to do it that way. But maybe we wanted to do something a little bit different. Maybe we wanted to find the area of an ellipse. So first of all, we'll go ahead and sketch it. Let's see. Sketching the ellipse. I wonder if I have an ellipse in my shapes here. I do. Look at that. Let's see how it works. Do I put it here and then start, or what do I do? Nope. Let's get rid of that. No, I kind of see how it works there. So maybe I don't. What if I can just draw an ellipse and then I can move it? Can I do that? I can. Look at that. I'm way too fascinated with this stuff. Okay. So there's my ellipse. And we'll just say, because we don't know, that this is distance out here is, oops. No, the distance is not oops. The distance is A. I want to go thin with this pen again. There we go. So the distance here is A. We'll call this distance up here B. So your major axis is A, your minor axis is B. And what we want to do is we want to find the area. So here's the thing. When we go to parameterize this, because we do need to do this in parameterization again, we're still going to use polar. Parameterize it. We're still going to go polar. Because we don't know these values, we just have to go with the generic A and B. So x on the x-axis, on the major axis here, is A cosine t. And then y on the minor axis is B sine t. And you could definitely go ahead and check to make sure that works. You know, if you let t equal 0, an angle of 0 here, if t is 0, cosine of 0 is 1, so that's A, that's this distance. Sine of 0 is 0, so there's no value for B. So that actually works, and you could go all the way around this ellipse and check that out. If you were to actually solve this and put it into an actual equation of ellipse, we did this a long time ago, you would divide both sides here by A and divide both sides here by B, so you would get x over A equals cosine t, and you would get y over B equals sine t. This is not necessary for the problem. It's just showing you that this puts everything into a standard form of an ellipse. If you square this side and you square this side, you would get x squared over A squared plus y squared over b squared, squaring this, adding together, and then of course you'd have to square the right side, so cosine squared plus sine squared would give you 1. And this right here is the standard equation for an ellipse, where whatever is under the x, this value a, is going to be on the x-axis. Whatever is under y is the length here on the y-axis. So the major and minor doesn't really matter, because you could have a major axis vertically as opposed to horizontally, but you do have to match the x with the a value here and the y with the b value up here. In any case, we're going to go ahead and show Green's theorem works for 1/2 of x dy minus y dx. All right, so 1/2. Again, we're going all the way around this thing, so it's still polar, so we're still going to go 0 to 2 pi. X was a cosine t. Dy is the derivative here, which is going to be b cosine t, minus y, which is b sine t, times the derivative of x dx, which is going to be negative a sine t dt. So again, hopefully what you can see is I have an AB, which are constants, in common. I can pull that out to the front, so I get AB over 2, integral 0 to 2 pi. I have a negative times a negative here, which is going to give me positive again, so I end up with a cosine squared t plus sine squared t dt, which of course then again is 1. So really what I have is AB over 2, integral from 0 to 2 pi of 1 dt. And of course the integral of 1 is just t, so I get AB over 2 t from 0 to 2 pi. 0 does nothing for us, so we plug in the 2, and you end up with AB over 2 times 2 pi. 2's cancel out, and what you get is pi AB, which is, if you remembered, if you didn't remember, that's fine too, the area of an ellipse. And if you really think about it, if A and B are the same, if this distance here is the same as this distance here, that means what we have is a circle. And if A and B are the same, what you would get is pi a squared, where a is the radius, or pi r squared, which of course is the area of a circle. Pretty cool stuff. Anyway, so there is your Green's theorem. And remember, to do this, we had to be positively oriented, which we were, because we were going from 0 to 2 pi. And we did that on the last problem as well. All right, so down at the bottom of your page, this is really the question. Why do it this way for simple things like circles and ellipses? Because we have much easier ways to find areas of circles and ellipses than this. And you probably wouldn't. The next example, however, is really, this is really the culmination of everything. And yes, you don't have anything written there. We're going to draw this in. So here's the concept. Let's go ahead and put this in black. So if I were just to start putting points out here, you can do your best to kind of copy what I'm doing. It doesn't really matter ultimately how many of these things you have. I got points all over the place. Now let's see how good I am at drawing. If I start kind of connecting these dots, what I'm going to form, assuming that my drawings are all straight, which they're not going to be, but whatever. It's supposed to be straight lines. I probably could have used the little line tool to do this. Would have been better. But this is kind of challenging and kind of fun. What I'm actually creating here is some kind of a odd looking polygon, whatever the heck it looks like. I don't know what that looks like exactly, but it's a polygon. Okay, it's got so many different sides to it. What do we got here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 sides to this polygon, so it's, what is that, a decagon of some kind? It's just not a regular one. Here's the idea. If I want to find the area of this region D, Okay, I still need to go around this thing in a counterclockwise fashion. But each one of these pieces of this polygon is linear. So this would basically be like C1, this piece would be like C2, this piece would be like C3, and all the way around. I only picked this to be C1. It doesn't matter where you start. But each one of these endpoints has a point associated with it. So this would be like the point x1, y1. This right here might be the point x2, y2, and all the way around. And I said we had, like, what did I say, 10 of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we have 10. So this one over here would be like x sub 10, y sub 10. And then all the way around. I'm not going to label every single one of them. But the general idea is if I could find the line integral of each one of these pieces and then add them up, I would really have the whole entire thing. So if I took, C1 plus C2 plus C3 all the way up to the end one, in this case we have 10, but normally we would just say Cn because we don't necessarily know how many we're going to have, then you would get the entire curve. And then if I took the line integral of those, line integral of C1 plus the line integral of C2 plus the line integral of C3, all the way up to the line integral of the last one, well, what that's going to give us is the area of the polygon. There we go. Fix this just a little bit here. I am trying to get this all into one video. I think we're going to be good. It's going to be a little over 30 minutes. All right, so let's see how it works. So if I just deal with the C1 part, I'm just going to deal with this part right here for right now. That would be 1/2 the line integral over C1 of x dy minus y dx. And once again, we're going to have to put this into some kind of parameters, but these are lines. So when we go to parameterize these, we're going to have to do our equation for a line, but we're going to have to do it in general here. So remember that the equation would be that x equals, where does x start? X starts at x1. And then x changes from here to here. Now, if we had numbers, we would just subtract the numbers. So if this was like 1 and this was 4, then we know x would change by 3, and it would be 3t. But we don't have that. So instead of numbers, we're just going to have to use the letters. Well, this is going to be x2 minus x1. That's the change, times t. And then y is going to be the same idea. It starts at y1. The change in y will be y2 minus y1 times t. All right, so we have our parameters set up. Let's go ahead and work out the integral. So it's going to be 1/2. And remember that these are standard linear pieces, parameters. So this is just going to go from 0 to 1. All right, so the first one is going to be x, which is this whole thing right here. So it'll be x1 plus x2 minus x1t times dy, which is the derivative of this thing here with respect to y. Well, remember that y1 is a constant. That's just a number. y2 minus y1 is also a constant, but it's multiplied by the t. So remember, if you took the derivative, if this was like a 5t, the derivative would just be 5. Well, instead of 5, it's y2 minus y1. So the derivative here is y2 minus y1. So this is like your x. This part is your dy minus y, which is this piece right here, y1 plus y2 minus y1 t times dx, which is the derivative of this piece. Same idea as the one down here. It's just going to be the constant out in front of t, so that's going to be x2 minus x1. That's your dx piece right there, that whole thing dt. All right, hopefully that makes sense. And don't worry, this will simplify. It's going to be a little messy up front here, but it will simplify. All right, so now we're at the point where we can take the antiderivative. So remember that this x1 is a constant. This y2 minus y1, that's a constant. The only thing that has a t in it is right here. And the only thing that has a t in it is right here. These pieces are constants. So that'll make things a little bit easier when we go to take the antiderivative. So we can bring this constant. We're not going to bring it out to the front because you'd have to be able to bring both of them from the same. You can't do that. We're just going to move it to here. So 1/2, oops, 1/2. So this is going to be y2 minus y1. Okay, it's just a constant. And then this piece right here, the antiderivative of x1, is going to be x1t plus, now this is a constant times t, so remember, raise the exponent, it's t squared, then divide by the new exponent, which is 2. So I'm going to get x2 minus x1 over 2 t squared. Okay, and we'll do the same thing over here. Again, I'm just going to bring this x2 minus x1 to the front instead of distributing it through. That's basically the idea, is what I'm trying to tell you there. And then this is going to be the antiderivative of y1, which is y1t. Antiderivative of y2 minus y1 times t. Remember, raise the t, it's t squared, divide by 2. So we're going to get y2 minus y1 over 2 t squared. And we'll evaluate that from 0 to 1. Alright, so let's go ahead and plug some stuff in here. Alright, so if I plug in, well, the good thing is if I plug in 0, I get x1 times 0 is 0, all this times 0, so this whole thing is 0 times this is 0. Everything goes away when I plug in 0, so really only have to worry about plugging in 1. So when I plug in 1, remember you're plugging in 1 for t, so you're going to get y2 minus y1. This is going to give me x1. If I plug in 1 here, that's 1, so it's really going to give me plus 1/2 x2 minus 1/2 x1. Okay, I'm only breaking this up to simplify it later. Same idea here, x2 minus x1, and then plugging the 1 in for t is going to give me y1, oops, not y11. Plus, plugging the 1 in here just gives me this, which is going to be 1/2 y2 minus 1/2 y1. Okay, let's go ahead and combine what like terms we can. 1/2 y2 minus y1. And here I've got an x1 and a minus 1/2 of x1, so that gives me a 1/2 x1 plus a 1/2 x2 over here, x2 minus x1. And then I've got a y1 and a minus 1/2 y1, so that gives me a 1/2 y1 plus 1/2 y2. All right, hopefully what you can see is I have a 1/2 in here that I could factor out. I have a 1/2 in here that I could factor out. So really I can pull a whole 1/2 out to the front, which is going to give me a 1/4. And then I have y2 minus y1, x1 plus x2 minus x2 minus x1, y1 plus y2. Okay, once we FOIL all this stuff, a lot of this stuff is going to simplify very quickly. So let's go ahead and FOIL this. So we're going to have y2 times x1, so that's x1, y2. Outside will give me x2, y2. Inside will give me negative x1, y1. And then last is going to give us negative x2, y1. And then just be careful here because we are subtracting this. So first times first is x2, y1, but it will be negative. So it's minus x2, y1. Outside x2, y2, but that again, that'll also be negative. So x2, y2. Inside is going to give me negative x1, y1, but that negative there makes it positive. So it's plus x1, y1. And then this is going to give me negative x1, y2, but that negative makes it plus. So it's plus x1, y2. All right, and let's see now what stuff might start canceling out. So let's see, I've got x1, y1, I'm sorry, x1, y2, and I've got another x1, y2. Those don't go away. x2, y2, minus x2, y2. These go away. Negative x1, y1, and a positive x1, y1. Those go away. And then I've got a negative x2, y1, and another negative x2, y1. Those two things are not going to go away. So it looks like what I have is 1/4. I have an x1, y2, another x1, y2, so I've got two of those. And then I've got a minus 2 of these, minus 2x2, y1. The 2's can be pulled out to the front, so that gives me 1/2 of x1, y2 minus x2, y1. All right, that's a really long way to go to get here, but what we've now done is we've shown that the integral over C1 is simply going to be 1/2 x1, y2 minus x2, y1. So if we actually knew what the values of these points are, I don't even need to do an integral at all. According to this, the integral over C1 of that one line segment is just going to be 1/2 x1, y2 minus x2, y1. Therefore, the idea would be, well, the integral for the C2 part would be 1/2, move all your indices. So that would be x2, y3 minus sorry, that's not right. Yeah, it is. I'm sorry. x2, y3 minus why am I drawing a blank? x3, y2. I don't know why that was so hard. But that's it. You're just going to keep shifting the indices, and you're going to do that all the way down till you get to the very last one, the integral over Cn. The last one would be 1/2, and then it would be xn y1 minus x1 yn. And that would be the very last one. So you would do that all the time. In this case, you would do 10 of them. But really, if you did 10 of these and then you added them all together, what you would really have is the area of the polygon. And that's actually really kind of a cool thing. So it's kind of taking Green's theorem and going backwards and kind of forcing it to line integrals. But these line integrals are really simple to do. Now, of course, this works if it's a polygon, if this is all linear pieces right here. And that's the general idea. All right, so we did it all in one long video. It's about 40 minutes long. That should be good enough for what you guys need to do. So enjoy.